Welcome to Module 1, Chapter 2, where we explore how modular product design serves as a powerful strategy for advancing circular economy goals. In this chapter, we'll look at how modularity enables products to be repaired, upgraded, and recycled, extending their life cycles and reducing waste. We'll discuss the foundational principles, practical strategies, and real-world examples that show how modularity creates value for businesses and society. By the end, you'll understand the drivers behind modular design, the challenges and opportunities it presents, and how it can be implemented to support sustainability and innovation in product development. This chapter will equip you with the knowledge to apply modular thinking in your own projects and organizations. In this chapter, we will cover the foundations of modular product design and its critical role in the circular economy. We'll begin by exploring the core principles and material strategies that make modularity possible, then examine how these principles support circular economy strategies and systemic approaches. We'll review case studies from leading companies to see modular design in action, and discuss the design strategies and tools that enable circular modularity. Finally, we'll analyze the benefits and challenges of modular design in the circular economy, helping you understand both the opportunities and obstacles in implementing modularity for sustainability. This agenda will guide you through essential concepts and practical applications, preparing you to apply modular thinking in real-world contexts. Foundations of modular product design and circularity. Modular product design is a foundational strategy for advancing circular economy goals because it enables products to be easily repaired, upgraded, and recycled. This approach extends product life cycles and minimizes waste, which is crucial for sustainability. Modularity emphasizes flexibility and longevity, allowing for more efficient management and optimization of resources. By dividing products into modular components, companies can simplify maintenance and upgrades, reducing the need for complete replacement and minimizing waste generation. This not only supports environmental goals but also offers economic benefits by lowering costs associated with repairs and upgrades. Frameworks like the 6R concept, reuse, recycle, reduce, recover, redesign, and remanufacture, guide sustainable manufacturing and help businesses transition from linear to circular models, maximizing the value of returned products and supporting resource efficiency. Integrating modularity with circular economy principles brings significant opportunities and unique challenges. Modularity enables the reuse of components and optimizes closed-loop supply chains, maximizing the value of returned products and supporting sustainable manufacturing. The 6R concept, reuse, recycle, reduce, recover, redesign, and remanufacture, provides a comprehensive framework for sustainable design. However, balancing intellectual property protection with the need for sustainable recovery and recycling can be complex. Innovative approaches to product family architecture are needed to address these issues, ensuring that modular products remain both competitive and sustainable. Overall, modular design supports the transition from a linear to a circular economy, enhancing the sustainability of product systems by integrating modularity with life cycle engineering and systemic thinking. This integration is essential for creating products that are adaptable, durable, and environmentally responsible. Core principles and material strategies for modular design. Design for disassembly, cradle to cradle, and standardization are essential principles for modular product design in the circular economy. Design for disassembly ensures products can be easily broken down into components for repair, refurbishment, or recycling, reducing costs and waste. The cradle-to-cradle approach advocates for using safe, circular materials that can be perpetually cycled, minimizing environmental impact and resource depletion. Standardization and interchangeability of parts are also vital, allowing for cost-effective upgrades and repairs, which extend product value and lifespan. By embedding these principles into product development, companies can create products that are easier to maintain, upgrade, and recycle, supporting longer life cycles and reducing environmental impact. These principles are the foundation for designing products that are both user-friendly and sustainable, making circularity achievable in practice. Eco-modular product architecture and life cycle analysis are critical for advancing modularity in the circular economy. Eco-modular design focuses on creating modular components that can be recycled or reused without full disassembly, conserving resources and reducing waste. Integrating life cycle analysis into design strategies helps optimize resource use and minimize environmental impact, ensuring that disassembly and recycling are economically viable. Legislative frameworks, such as the EU's design for disassembly criteria, promote easier disassembly and extended product lifespans. Diagnostic tools that assess disassembly, modularity, and standardization provide valuable insights for redesigning products to enhance their circularity and durability, supporting a shift to systemic regeneration and long-term use. These approaches ensure that products are designed with their entire life cycle in mind, from material selection to end-of-life recovery. Material selection, mono-material design, and life cycle thinking are fundamental to modular product design for circularity. Choosing sustainable materials like bioplastics, recycled metals, and non-toxic adhesives supports modularity and reduces environmental impact. Mono-material product design uses bio-based, circular, and biodegradable polymers, simplifying recycling by allowing chemical recycling of single monomers. This approach enhances material circularity and reduces the complexity of separation and reprocessing. Life cycle thinking encourages designers to anticipate how materials will behave during use, repair, and end of life, minimizing environmental impacts and maximizing product value over time. These strategies support the creation of flexible, long-lasting, and easily upgradable products that align with circular economy goals. By considering the entire life cycle, designers can ensure that products remain valuable and sustainable throughout their use. The use of indicators and computational tools is essential for making informed, sustainable material choices in modular product design. The Material Durability Indicator, or MDI, combines chemical and mechanical durability with environmental impacts, providing a balanced and holistic framework for selecting materials that will last and have a lower environmental footprint. Advanced computational intelligence methods, such as neural networks and genetic algorithms, help designers optimize material choices by identifying properties that minimize environmental harm while maximizing sustainability. These tools allow for the exploration of a wide range of material combinations and enable accurate predictions of their lifecycle impacts. By leveraging data-driven approaches, designers can ensure that materials not only perform well, but also contribute positively to circularity goals, accelerating the development of products that are both innovative and environmentally responsible. Overview of circular strategies and their systemic impact. Recycling, refurbishing, and reuse are essential strategies for improving resource efficiency and reducing environmental impacts in the circular economy. These approaches keep materials in circulation, minimizing the need for new resources and cutting waste. Case studies in electronics and packaging demonstrate that circular strategies lower raw material use and energy consumption, delivering clear environmental and economic benefits. Advanced techniques like closed-loop recycling and upcycling further enhance material circularity, keeping materials at their highest value and supporting a sustainable, regenerative system. A systemic approach, including life cycle assessments and resource efficiency indicators, is crucial for a successful transition to a sustainable circular economy that operates within planetary boundaries. By adopting these strategies, organizations can significantly reduce their environmental footprint and promote long-term sustainability. Introduction to real-world modular design examples. Fairphone is a leading example of modular design in the electronics industry, challenging the conventional short life cycles of smartphones. Devices like the Fairphone 4 and 5 feature user-replaceable modules, battery, display, cameras, USB-C port, and speakers, allowing easy repairs with simple tools. The company uses fair trade gold, recycled tin, and plastics to reduce environmental impact and promote ethical sourcing. Fairphone supports the circular economy by extending product lifespan and offering long-term software updates. Providing spare parts and repair tutorials fosters a repair culture, empowering consumers and combating planned obsolescence. This approach not only reduces electronic waste but also inspires broader industry change toward more responsible production and consumption patterns. Fairphone's commitment to transparency and ethical sourcing sets a new standard for sustainability in the tech sector. Fairphone's modular approach presents both engineering and business challenges, but also drives significant industry impact. Designing a modular phone that is durable, visually appealing, and affordable requires complex engineering solutions and careful material selection. Ensuring the long-term availability of spare parts demands precise supply chain management and forecasting. Despite these hurdles, Fairphone's commitment to sustainability and transparency in material sourcing and factory conditions highlights its ethical and circular economy commitments. By empowering consumers to repair and understand the devices, Fairphone fosters a deeper connection with technology and demonstrates a viable market for sustainable, repairable electronics, providing a blueprint for reducing environmental impact and inspiring industry-wide change. The company's success shows that modularity and sustainability can go hand in hand, even in competitive markets. IKEA's modular systems, such as PAX wardrobes and Kallax shelving, allow customers to customize furniture by adding or removing sections to fit changing needs. This flexibility means that instead of discarding an entire piece of furniture when circumstances change or a minor issue arises, customers can modify or repair their existing items. Replacing or repairing individual components reduces waste and prevents discarding entire pieces. Interchangeable parts and a wide range of components empower prolonged product usability and reduce landfill waste. IKEA's Buy Back and Resell program promotes reuse and recycling, shifting consumption from a linear to a circular model. These strategies support flexible, sustainable living and encourage a more responsible approach to home furnishing. By making modularity accessible and affordable, IKEA helps mainstream circular economy principles in everyday life. IKEA's People and Planet Positive strategy aims for circularity by 2030, with modular design as a key enabler. All products are being designed with circular capabilities, using renewable or recycled materials, and services that help customers prolong product life. IKEA also explores materials that are easier to recycle and components that can be efficiently disassembled. Modular furniture offers personalization and cost savings, as pieces can be adapted rather than replaced. These efforts help customers make environmentally conscious choices and support longer product life cycles. By promoting sustainable consumption and offering innovative services, IKEA is helping to shift consumer mindsets towards circularity and responsible resource use. This approach not only benefits the environment but also enhances customer satisfaction and loyalty. Dell incorporates modular design in laptops, desktops, and enterprise hardware, focusing on repairability, upgradability, and recyclability. Products like the Latitude series allow easy access and replacement of parts such as RAM, storage, and batteries, extending device life and reducing costs. Dell's closed-loop recycling recovers plastics and rare earth magnets from old devices for use in new products, supporting resource recovery and circularity in IT hardware. The Concept's Lunar laptop showcases extreme modularity with tool-free disassembly, enhancing repairability and component reuse. These strategies not only reduce e-waste but also demonstrate Dell's commitment to sustainable innovation and responsible production in the tech industry. By making repair guides and spare parts accessible, Dell empowers customers to manage their IT assets more sustainably, aligning with corporate social responsibility goals. Dell's holistic approach to design for circularity begins with the selection of sustainable and recycled materials, prioritizing durability and energy efficiency from the start. Products are designed for easy repair, upgrade, and recycling, with accessible repair guides and spare parts empowering customers to maintain their devices. This approach reduces e-waste, conserves resources, and lowers the overall environmental footprint. Dell's strategy aligns with corporate social responsibility goals and demonstrates a strong commitment to sustainable innovation, benefiting both businesses and the environment. By integrating circularity into every stage of the product lifecycle, Dell sets a benchmark for responsible design and production in the technology sector. Their efforts show how modularity can drive both environmental and economic value. Herman Miller's iconic office furniture, like the Aeron chair, uses modular design with distinct, replaceable parts. Components such as the seat pan, backrest, and armrests can be individually replaced or upgraded, extending product lifespan and reducing waste. This design supports circular supply chains by enabling material recovery and minimizing landfill waste. The company's design for environment approach uses recyclable materials and ensures ease of disassembly, facilitating proper recycling and supporting sustainable material cycles. Herman Miller emphasizes non-toxic, durable materials that support sustainable cycles and long product life. The design focuses on longevity and repairability, maximizing resource use and reducing waste. Take-back programs and partnerships with remanufacturers enable effective recycling and remanufacturing, closing material loops. This comprehensive strategy combines modular design with robust end-of-life solutions, demonstrating a commitment to sustainability and responsible manufacturing, and making their products an investment in both comfort and environmental stewardship. By focusing on material recovery and product longevity, Herman Miller sets a standard for sustainable practices in the furniture industry. Their approach ensures that resources are kept in use for as long as possible, supporting a truly circular supply chain. Volvo uses modular battery packs in electric vehicles, enabling selective replacement and reducing waste and repair costs. Modular design supports second life applications for batteries and facilitates recovery of valuable materials like lithium and cobalt. Shared vehicle platforms, such as SPA and CMA, allow efficient manufacturing and easier upgrades across models. These strategies reflect design for circularity, making EV ownership more sustainable and economically viable, and supporting a circular approach in the automotive industry. By focusing on modularity, Volvo is able to extend the life of vehicle components and reduce the environmental impact of electric mobility. Their commitment to sustainability is deeply embedded in their engineering philosophy. Volvo's modular design in electric vehicles supports easier maintenance and future upgrades, enhancing vehicle lifespan and performance. The company integrates sustainability into engineering, focusing on minimizing environmental impact throughout the vehicle lifecycle. Volvo's approach covers design, use, reuse, and recycling, promoting a circular automotive industry for electric mobility. This strategy ensures that the shift to electric vehicles is as sustainable as possible, benefiting both consumers and the environment. By adopting a life cycle perspective, Volvo demonstrates how modularity can drive sustainability and innovation in the automotive sector. Their efforts help set new standards for circularity in transportation. Design strategies and tools for circular modularity. User-centered design and systems thinking are essential for successful modularity in the circular economy. User-centered design emphasizes empathy with users, ensuring modular features are functional and easy to use, which promotes repair and upgrades for longer product life. Systems thinking considers the entire product lifecycle, making sure components can be disassembled, reused, or recycled, thus optimizing sustainability and reducing waste. These approaches enhance product adaptability, support sustainable consumption, and help designers create solutions that are both user-friendly and environmentally responsible. By integrating these strategies, designers can develop modular products that meet user needs while advancing circular economy goals. This holistic approach ensures that modularity is practical, effective, and aligned with sustainability objectives. Computer-aided design, CAD, tools and digital prototypes are vital for developing modular products that support circularity. CAD tools enable detailed digital modeling and testing of modular structures before production, allowing designers to identify and address potential issues early. Digital prototypes allow for iterative improvements based on realistic performance simulations, refining designs for strength, assembly, and lifecycle performance. Circularity metrics, such as the Material Circularity Indicator and Product-Level Circularity Metrics, provide quantitative data to guide design decisions towards sustainability. These tools help designers identify areas for improvement and validate the circular credentials of a product, ensuring alignment with circular economy principles and supporting continuous innovation. By leveraging these tools, companies can create products that are both high-performing and sustainable. Strategic integration of design approaches and advanced tools is crucial for fostering innovation and sustainable production in the circular economy. By shifting from linear to circular models, organizations can enhance resource efficiency and sustainability. Advanced tools encourage innovative product design, enabling the development of solutions that maximize value and minimize waste. Integrating these approaches supports the creation of new sustainable business models for responsible production and consumption. This comprehensive strategy contributes to more sustainable consumption and production patterns across industries, driving innovation and supporting the essential shift to a circular economy. By embracing strategic integration, companies can lead the way in sustainable innovation, benefiting both business and society. Benefits and challenges of modular design in the circular economy. Modular design offers substantial environmental and economic benefits within the circular economy framework. By enabling easy replacement of parts, modularity extends product lifespans, which reduces the need for new materials and cuts down on waste. This approach supports innovative business models such as leasing, refurbishment, and resale, allowing products to generate value across multiple life cycles and boosting economic viability for companies. In sectors like construction, modular design optimized for reuse can reduce greenhouse gas emissions by up to 88% compared to traditional recycling methods. Modularity also supports efficient closed-loop supply chains, maximizing resource efficiency and profitability by keeping components in circulation. These benefits make modularity a powerful tool for companies aiming to reduce their environmental impact while creating new opportunities for growth and customer engagement. While modular design brings many benefits, its adoption is not without challenges. One major hurdle is the increased complexity during the initial design phase, which requires meticulous planning and execution to avoid performance compromises. Designers must ensure that modular products meet high standards for durability, functionality, and user experience. Consumer education is also crucial, as users need to understand how to participate in circular economy models and take advantage of modular features. Collaboration among designers, manufacturers, and end users is essential to overcome these challenges. By working together, stakeholders can ensure that modular products are not only technically sound but also appealing and accessible to consumers. This collective effort is necessary for modularity to fulfill its promise of supporting a more sustainable and circular economy. Modular product design is a transformative strategy that enables easy repair, reuse, and upgrades, supporting sustainability and reducing waste throughout a product's lifecycle. By embedding modularity into the design phase, companies can foster longer-lasting relationships with consumers, lower environmental impacts, and reduce inefficiencies. Modular design is a key enabler for the transition from linear to circular economy models, promoting resource efficiency and long-term value. Adopting modularity benefits both businesses and the planet by encouraging innovation, reducing environmental impact, and supporting sustainable growth. Products last longer and require fewer resources, thanks to easier upgrades and repairs. Modular design also inspires new business models and creative solutions for sustainability, making it a cornerstone for future-oriented, responsible product development. Thank you for your attention. Next, we continue with Module 1, Chapter 3.